You ever wonder what's really going on inside an AI? Behind all the hype and the headlines. Well, whether we're talking about the simplest little gadget or the most powerful supercomputer, it all boils down to one single powerful idea. And today, we're pulling back the curtain on that secret ingredient, the intelligent agent. Okay, let's just think about this for a second. Picture a little robot vacuum cleaner, bumping its way around your living room floor. Now picture a state-of-the-art self-driving car navigating the chaos of a downtown street during rush hour. I mean, these things seem like they're from completely different planets, right? Well, what if I told you that deep down, they're built on the exact same foundation? Yep, that's the big secret. They are both intelligent agents. And this isn't just a piece of trivia. This is everything. If you can really wrap your head around this one concept, you'll have the master key to understanding how pretty much every piece of modern AI actually works. So here's our game plan. We're going to start with the absolute basics. What even is an agent? Then we'll get into what makes it smart, this crucial idea called rationality. From there, we'll explore the world it has to live and operate in, its environment. We'll look at the different blueprints for actually building these agents, and we'll cap it all off by looking at the holy grail, the learning agent.
All right, first things first, let's start right at the beginning. What exactly is this fundamental building block of AI that we keep calling an agent?
Okay, so the official definition sounds a little academic. I get it. But the idea behind it is incredibly simple. An agent is just anything that can perceive its surroundings with sensors and then do something to those surroundings with actuators. It's really just a continuous loop of perceive, then act.
And this diagram here just nails that idea perfectly. You've got information flowing in from the world through sensors. The agent processes that information, and then it takes an action that affects the world, pushing something back out through its actuators. Just think of sensors as its eyes, its ears, its sense of touch, and the actuators, those are its hands, its feet, its voice, anything it can use to make a change. And please, don't think this is just about physical robots. For sure, a robotic agent, like our vacuum cleaner, uses cameras and infrared as its sensors to see walls and dirt, and its motors are the actuators that let it move and clean. But a software agent is just as real. Think about it. Its sensors might be your keystrokes or data coming in from the internet, and its actuators are what it uses to display things on your screen or send information back out.
So if pretty much anything can be an agent, what separates a good one from a bad one? I mean, what makes an agent smart and not just a rock? The answer is this really important concept called rationality.
And at its core, it's a beautifully simple idea. A rational agent is just one that does the right thing. But of course, for an AI, the right thing is way too vague. We need to define that with a lot more precision. And here it is. In the world of AI, doing the right thing simply means choosing whatever action is most likely to get you the highest score. It's like the agent is playing a video game. We, the designers, give it a performance measure, a way to score points, and the agent's entire purpose in life is to do whatever it takes to maximize that score. Let's go back to our trusty vacuum bot. This little table you see here, that's its brain. It's what we call an agent function, and it just maps what it sees to what it does. So if its perception is, I'm in location A and it's dirty, the rational action that gets it the most cleanliness points is to suck. But if it sees, I'm in location A and it's already clean, well, the rational action is to move right and find more dirt. Every single decision it makes is driven by that one goal: get the highest score. Now, an agent can't be rational in a vacuum. Sorry, couldn't resist that one. But really, the context that an agent operates in, its environment, is just as critical as its own internal programming. You can't separate the two. So to deal with this, AI designers use a handy tool called the PAS framework. It's how you write a job description for an agent. PAS stands for Performance, Environment, Actuators, and Sensors. For a self-driving taxi, its performance is measured by a safe, fast trip. The environment is the total chaos of roads and traffic. Its actuators are the steering wheel and pedals, and its sensors are the cameras and GPS. You absolutely have to nail this down before you write a single line of code. And it turns out, not all environments are created equal. They have different properties that make them easier or harder to deal with. First up, is it fully or partially observable? In a fully observable world, like a chess game, the agent can see the entire state of the world at all times. But in a partially observable world, like driving, the agent has blind spots. It can't see around a corner, and it certainly can't read the minds of other drivers.
Next question, is the environment predictable? A deterministic world is like a crossword puzzle. If you perform an action, you know exactly what the result will be. But most of the real world is stochastic. It's got randomness baked in. Our taxi can signal to change lanes, but it can never be 100% certain that another car won't suddenly swerve and block it.
And finally, does the world wait for the agent to make up its mind? A static environment, like that crossword puzzle again, will patiently wait for you. But a dynamic one is always changing. While our taxi is busy processing data and thinking about its next move, the rest of traffic is still moving. The lights are changing. The world doesn't hit pause. This makes the challenge exponentially harder.
Okay, so we know what an agent is, we know its goal is to be rational, and we know what kind of world it's living in. So how do we actually, build its brain? Let's check out a few of the common blueprints, starting with the most basic and working our way up.
The simplest design is this simple reflex agent. You should think of this as a pure knee-jerk reaction. It has no memory, no planning, just a list of if-then rules. If the car in front slams on its brakes, then I slam on my brakes. If the floor is dirty, then suck. It only knows what it's seeing this very second.
Now, that's obviously pretty limited. So the next step is to give it a memory. This is a model-based agent. It maintains an internal model of how the world works, which lets it keep track of things it can't see right now. For our vacuum cleaner, this is a huge upgrade. Now it can remember which parts of the house it's already cleaned, making it way more efficient.
And this is where things start to get really clever. A goal-based agent doesn't just react to the world, it actually has a goal it's trying to achieve. So before it acts, it can ask itself, will doing this get me closer to my goal? This simple question is the birth of real planning and foresight in AI. But what happens when there's more than one way to reach the goal? That's where the utility-based agent shines. Utility is just a fancy word for happiness or satisfaction. This agent can weigh different outcomes to see which one is not just good, but best. It's not just asking, can this get me to the goal? It's asking, which path to the goal is better? Which one is faster or safer or more efficient? This is how an agent learns to make sophisticated, nuanced choices in a complex world. So we've climbed the ladder from a simple reflex all the way up to a sophisticated agent that can weigh its options. But every single one of them relied on rules that a human programmed in. The final, most powerful step in this evolution is to create an agent that can learn to write its own rules. You can think of a learning agent like a pro athlete with a personal coach. The performance element is the athlete on the field, actually taking the actions. The critic is the coach watching from the sidelines, giving feedback on how things are going. That feedback goes to the learning element, which is the part that figures out how to tweak the game plan for next time. And the problem generator? That's the coach in practice, yelling, try a new play. It pushes the agent to experiment and explore, helping it learn even faster. This whole loop is the engine that drives modern machine learning. And that really brings us to the biggest, most fascinating question of all. When you design an agent whose very purpose is not just to follow the rules you wrote, but to learn, adapt, and invent new strategies all on its own to achieve a goal, well, at what point do you stop seeing it as just a complex program and start seeing the genuine beginnings of intelligence?